Good evening, everyone. Today we have with us Professor Neeraja Dashaputre. Professor Neeraja Dashaputre completed her undergraduate studies in chemical technology from Institute of Chemical Technology, Mumbai, and obtained her doctoral degree in organic chemistry at University of Maryland, USA. She worked as a faculty at Claremont University. Currently, she is a faculty at IISER Pune. Her research focuses on pedagogy development for teaching chemistry. Today, she is going to discuss with us the science behind colors. Let's welcome her with a round.
There is a slight correction. I am a principal technical officer. I look after the curriculum and how to teach science at ICER Pune. So when I got this invitation from the organizers, I was a little puzzled because I almost thought, what am I going to talk? Like an experimental chemist, trained as experimental chemist, what am I going to talk to young women who are really, amazing at mathematics and statistics and are trying to, learn some fascinating things here. And then two topics came to my mind. One was entropy, which is basically like everything in the world is governed by entropy, right? In the universe is governed by entropy, and it has its basis very much in statistics. And then the other topic that came to mind was color. So I thought of moving the very math talk towards a little sciencey talk. So today we'll talk a little bit about science more than maths, I think. So I think all of you know about ICER. I don't need to say anything more, right? One thing at ICER Pune which we have is an outreach wing. And I would say it's a large team, many people, I think more than 50 of us work towards how to communicate science and maths to young kids, also to professors. So like how do you really communicate science such that it becomes accessible? I don't know how many of you have seen this YouTube channel and educational resources, but do go to the website. It's called Science Activity Center at ICER Pune. We have many toys, many activities and resources. Even for teaching mathematics, we have documented some of them. So one of the core philosophies I'll think of the team is that science should be accessible to all. It shouldn't be limited to people who have access to fancy technology. So we try to come up with science toys that can explain science, using everyday material. We believe that science is everyday, or rather science is what makes this world, right? So it should be possible to demonstrate it using everyday things. So for example, this is one of the gadgets that the team has come up with. It's a fidget spinner, right? But when I spin it, basically a magnet, a moving magnet from on a coil. Everyone can see that small LED glowing, hopefully, right? So that's one thing we have. The other many toys. Again, this is another one where you can see just using simple magnets, ring magnets, you can levitate a pen, trying to explain how maglev trains work. Okay, so that's the idea. And the other core idea I think that the team believes in, and I do believe in, is that science should be taught in the way it works. So it's not just a bunch of facts, it's not just a bunch of laws, it's not just, you remember this law, you remember this principle, and you've learned it. Rather, we need to teach students, starting from school, how to question, how to design experiments, how do you verify your hypothesis, and then do you really believe what you see, So science has to be an evidence-based practice. And that's what we try to teach teachers. So we also work with a lot of teachers, starting from school teachers to undergraduate teachers, on how do you teach science. So we do workshops for them. Okay, so coming to today's topic, which is color. I got trained as a chemical technologist, and my specialization was in color chemistry. So when I think of color, I actually think like it's a phenomena that really governs how we see the world. Right? We perceive the world through color. If we think about the science of it, there is, of course, physics involved, there is chemistry involved, there is biology has to be involved because you're seeing color. But there's a lot of mathematics as well, and we'll try to think about, how we go about it. In fact, in the previous talk, you were trying to come up with applications of a mathematical concept. towards the end when we were thinking about where all fractals can be applied. In this one, we'll try to hopefully see the applications and see, and maybe I'll pose a question for all of you to solve that humanity hasn't been able to solve yet. How can you apply mathematics to color, and how can we really represent color such that humans perceive it? Okay, we haven't been able to solve it yet. Maybe one of you will be that person solving it. Okay, so we have to start from Isaac Newton. He was the first one who basically showed that color is, the white light is made up of 7 colors. It wasn't that people hadn't seen that before, right? People had seen rainbows, people had seen, maybe soap bubbles which had these colors, but actually Newton's genius lies in the fact that he used a prism inverted again, right? So there was one prism, he put another inverted prism in front of it and then showed that the 7 colors can, give back your white light. And that's really proved that, white light is made up of 7 colors. Fun fact, he didn't see 7 colors. He observed only 5, but he loved the number 7 so much that he added 2 extra colors to it. The orange and the indigo were added later because there's something mystical about the number 7, I don't know what. So we all know the spectrum of light. This is something you must have studied. Today's talk, we are going to focus on 400 to 700, not, there is of course spectrum beyond there and beyond here on this side, there is long range, radio waves and other things, but let's focus on this 400 to 700 because that's what makes up our world, right? Okay, so we know that anything that when it absorbs light, right, you get an absorption spectrum. So this one, can you guess the color? What will this particular object have as the color? Green, wonderful. So that's your chlorophyll spectrum. So chlorophyll, oh, I think I gave you the answer right there, right? Yeah. Okay. But you can see that it is absorbing in the blue and the reddish or yellowish region, but the color that you see is what it doesn't absorb, in fact, what it reflects, right? That's the green color. Soon what you will see is that this one-dimensional representation of color is no longer useful. Because where are the brown hues or where are the pink hues or other colors that we really see with our eyes, we can't just trust this spectrum. We have to add some other dimensions to it. And that's why very often you'll also see luminescence added to it, right? So luminance basically will tell you how much light there is. So now we have gone from just X axis to now X and Y axis towards representing color. Right, so now you can see a little bit of browns appearing where there is lesser light and so on and so forth. But again, slowly we'll see this is also not the best way to represent color. And that's the challenge that we have for today. Okay, how do we see color? Everyone knows. What do I have in my hand? 3 primary colors, right? You have R, G, and B. In fact, when you see, let's say, oh, can you all see the green light? Okay, the moment I add the red one, what color do we see here? It's yellowish orange, right? And the moment I add the next one, it almost appears white, right? So we have this RGBA together working, giving you the white light. In fact, if you can see the shadow colors, now what are the shadow colors here? Okay, tell me from top, what do you see? Okay, cyan, magenta, and yellow, right? That's something that we have always studied in the color wheel, right? In the additive mixture. So if I now close the red one, what does the shadow look like? Magenta and yellow. If I close the blue one, what does the shadow look like? Cyan and magenta. So you can actually see the color wheel in front of your eyes if you have like an RGB light. Now here is the problem with human vision, right? I won't be able to detect this yellow color separately from another yellow color bulb. So let's say that bulb, if it was right here, I wouldn't be able to tell you whether that yellow color is coming from the addition of these two, versus a separate yellow source, right? And that is one of the, I think, beauties as well as a challenge when it comes to representation of color. It's nice that we cannot, differentiate between various sources of color. Otherwise, it will just imagine how many shades you would see and how confusing the world would look like, right? So when we think about our vision, we have 3 cones. Do you remember your biology lessons? Okay, so what are these 3 cones? So let's call them short, medium, and long range cones, right? We have like 6 million of them in our eyes. We also have rod cells. Rod cells are basically going to tell us whether we see light or not. So it's sensitive to presence or absence of light. Cones are the ones that are sensitive to the presence or absence of color, right? Now, what we have here, okay, can you see how it's distributed between 400 to 700? The short range is responsive to blue light, right? Whereas the mediums and the long range are kind of situated between 500 to 700, responsive to the green and red light. Okay? When I see something, the corresponding cells or the corresponding cone cells in my eyes are going to get activated. Depending on which cone cells are activated, or right, depending on which of these source am I really looking at, my brain will get a signal and I'll recognize the color, right? So now if I want to see a yellow color, which of these are really activated? For yellow, we just saw it was medium and long, right? So I should have medium and long range cells activated, or rather they're being used up, or they're getting tired looking at, and then I'll think of it as the yellow color, right? Okay. In fact, other animals don't have the same number of cones that we have. You must have seen this, that dogs have 2 cones, so they have a different dog's view, whereas when it comes to birds, birds actually have sometimes 4, sometimes 5 types of cones. So they also have a UV cone. So their world looks very different. So this is how we perceive the bird, whereas this is how the bird will perceive itself. Right? So it's very colorful world for the birds. At the same time, if you think about bees also look at the world in a very different manner, right? What do we have here? This is how the flower will look to us. But bees have a range from 300 nanometers to around 650 nanometers. So their worldview is just around in the center where the nectar is. Okay? So the point I'm trying to say is that based on how the structure of the eye is, or how the different cone cells and different rod cells and the different types of responses they give, the world is going to appear differently to that particular species. And so when we think of humans and when we have to model how color looks to us, we have to think about all these things, right? And people have tried modeling colors. So this is like from early 1600 or 1700s, various different models came to be where people tried to map color for us. Now, how do you find color? And most of these are no longer useful, right? But it's good to see that how different artists, different scientists or color scientists tried to map these things together. Okay, so people wanted to map color and people wanted to study how should you come up with representation of a color, because unless we represent something properly, we cannot standardize it. I mean, imagine like if I have a red, green and yellow signal in Pune, if it looks differently than the one in Bangalore, then people are going to get confused, right? So you have to have standards, and that's why these experiments were first done by Wright and Guild. Coincidentally, I think it is only one or very few of the cases where 2 scientists did experiments completely separately, but their results matched, tremendously well so that they could publish it together. So they didn't contact each other before, they were independently working with different sets of people, and they together came up with these experiments. So what were the experiments about? Okay, So what they did was they asked people to come up with a color match. So they worked with various, I think Wright worked with 10 people, Guild worked with 7, okay? And that's why the Wright and Guild model is based on 17 as the number of participants. But what they asked the people to do was that on one side there was one color shown, that is yellow. And it's very simple. On the other side, they had to use primary lights, the blue, green, and red lights, to really match the color that is being shown on the other side. So how would you, turn on the knobs such that everything here matches here? So what are they really doing is they're trying to add up these things such that these two things match. Now everything worked well except for some colors you couldn't come up with a match. So the truth is that human eyes can actually detect more than 1 million shades of color. So when you have to perfectly match, it was impossible for the human subjects who were part of that experiment to come up with an exact match. So for example, for 520 nanometers, they just couldn't come up with a combination of these three such that it matches it perfectly. So what did they have to do was they had to add a reference light from the, from their sample point. In a way, they're subtracting this from the equation. So now if you think about modeling this, like you have 3 variables and you have various coefficients, that is how much you have turned on the knobs. You're trying to see the addition such that you come up with the color. But in this case, one of the coefficients is going to be negative because you had to add something on the other end, that is the reference side. And that was the problem. So, and why does this problem really arise is because we are not sensitive to all colors. Like human eyes are not sensitive to all colors equally or all wavelengths equally. So our sensitivity actually is peaked around 550 to 600 nanometers. Here and here, our eyes are not sensitive. So you had to also think of, how that will affect your mathematical model. I hope I'm making sense. Okay. So in fact, when these were plotted, they observed that for red, they had to go, have negative coefficients. So let's say that I take some lambda of 500 nanometers. I have these long, medium, and short coefficients based on this normalized, and I go on plotting. I'll come up with a surface, a 3D surface rather, where this is now along this boundary are all my primary colors, right? There is a problem with this representation because as you saw that for all the colors that are visible to human eye, we couldn't come up with coefficients that are just positive. So in fact, when they tried to map it first, it was a lot in the negative region as well. Now, mathematically, it makes sense to have a negative coefficient, but physically it doesn't make sense because how do you remove light from something? Adding light is one thing, but removing light it's difficult physically. So then later on, they did some operations, transformed it such that everything right now lies in the positive positive quadrant. Okay, now here is the problem. After that, multiple models have come up. So this is around 1930s work, okay? So around 1930s, we are now, a century ahead. Multiple different models have come up. So Adobe came up with its own RGB model. Now there is this sRGB model where everything is linear and other things. But I mean, everything could be added linearly such that, let's say for any 2 points on the on this curve, if I take a middle point, I can actually do C1 plus C2 equal to C3, like a linear operation on it. The problem is it still can't map everything that we see. Every time you have a color, you get the next best closed match if it doesn't match. So all of our computers, all of our displays are currently working on this particular chromatopsity diagram, but it's not the best one yet. So you may think of something that you can really represent colors how humans see it. Okay, So just to give an example, I want you to stare at that circle for like 20 seconds. Don't blink your eyes, don't do anything. Let's just stare at it for like 20 seconds. Now, what do you see? You see a bluish green color, right? A rather greenish color. The reason why I wanted to show you this is that because the perception of color is very human phenomena, what happened now? What do you think happened? Why did you see that? Why did all of us see that color? Okay. Uh, okay, I'll put it the other way around. When you're looking at the red color, the corresponding cone cells were constantly focused on that red color. They were getting tired. So when you removed that red, the other cells were still, the other two cone cells were still, able to really respond quickly. But since the red cone cells were really tired, they didn't respond as quickly and you were not able to see that red. So that's why you were seeing the other two, which was green and blue, right? Now if you again see, it will start looking white because now your red cells have had time to come back to normal. Right? So perception of color is extremely human phenomena. In fact, there is this joke that many people make, and I think somewhere it's true, is that women can actually distinguish between many colors as compared to men. Right? They like, there is pink and there is fuchsia and then there is salmon and there is, and men don't have these many color shades in their palette. Right? The reason is that it's also linked to the chromosome. We do have an X chromosome since we have two of them, XX. We actually are better at identifying color as compared to men. At least the red ones, not the other ones, but the red ones we can actually look at it differently. So all of these factors have to be accounted when we have to model something that represents color. And in fact, when you see like really nice art, you will see that the artists have thought about it. So here is the famous shadow by Van Gogh. What shadow color is this? Blue, right? It's not black. The same thing here. Here is the shadow of green or shadow of red. Here it's still in the bluish range. If it was a grayish black, the painting would have looked really bad. So artists are also thinking about what, and in fact they can make better drawings because they have a good understanding of this phenomena. And to think about colors and how colors have come across centuries, this is Altimara bison. So this is, now we are starting to slowly go towards chemistry. So this is Altimara bison. It's, I think, a cave in Spain. Really old cave. It has red color in it. And in that era also, people knew that iron compounds, when oxidized, can give you that red color. This is another way people obtain color long back. So this is an Arabian rug. Where do you think this comes from, this red color? So it's not from iron, but this one came from some bugs. It's called Armenium chinchillas, right? So those are the bugs where they killed the bugs, insects, dried them and took their pigment. On the other hand, have you seen this one? So this is called Indian yellow. How do you think we got Indian yellow? Not turmeric. So there is a funny story. So most of our Pattachitra drawings that use yellow used Indian yellow in it, and the way they got that Indian yellow was actually by feeding cows a lot of mangoes. Right? They fed the cows lots of mangoes and lots of mango leaves, young mango leaves, and collected the urine. And this is dried, urine, and a lot of pigment came from the urine that they collected it to paint these Pattachitra. Okay, how many of you have been to Aurangabad? You should visit it sometimes. It's a very nice place. So these are the Ajanta caves. So this is the Padmapani image there. Which color is not there in this image? Blue, right? So blue was in fact extremely difficult to come up with. We didn't know how to come up with a blue pigment. It was a rare kind of a thing, and we could only import really small amount of it from Turkey or some other places in the east. And that's why you see very little blue in most of these paintings. So the only place where blue was really prevalent were these Egyptian paintings. They had figured out how to use copper and have a pigment that looks bluish in color. But we do have blue here, right? So where is this blue coming from? Why wasn't it possible to use? Because Indians had peacocks, right? Anybody knows where does the peacock's blue come from? Okay, so it's in fact, so I have a peacock feather here. It's in fact the interference of light. There is no blue pigment in it. It's just how light is interfering with the little scales that are there on this particular feather. So right now you can see the blue. In fact, if I do this, what color is this now? Almost black, right? This is blue. This is black. Why so? Because I'm breaking that interference pattern for light. Right? So it's important to also look at the structural features, and these are called structural colors for a reason. All those scales, how light interacts with it will give you that nice blue. In fact, there's only one true blue species out of all of these millions of species in the world. There's only one particular species that can come up with a true blue. It's this butterfly, Olivia butterfly, that has this blue patch, which is a blue pigment. Which was also sometimes used by queens, where they had to literally grow those many butterflies to have. So this is a hair clip from China, where they had to grow these many butterflies to really take that pigment out. But that's the story of blue, and let's continue on that story. So what questions come to your mind when you look at this? When you look at this picture, any questions that come to your mind? Is it even real? Okay. Hey, nobody thought of I want to go here, when will I go here kind of questions. Come on, you're young people. That would be the first thing I will think about. When will I get to go on a vacation, right? But yeah, so the two questions that should appear and that did appear in two people's mind. One was, why is the sky blue? The second one is, why is the water blue? So who asked the first question? Anybody remembers the name? Okay, it's okay. No need to remember. So it's Tyndall effect, right? So Tyndall was a mountaineer, and he basically looked at sky many times to really figure out that it looks differently at the time of sunrise, looks very different at the time of sunset, and during the day it's all blue. Why is it blue? So why is it blue? Scattering. So we know that it's scattering, but if you look at the spectrum of the blue sky, what is the highest intensity? It's blue violet, right? So why don't we see a violet sky? So maybe our eyes are sensitive. Any other guesses? What do we have around the earth? Ozone, right? So most of the violet actually gets absorbed, right? So here what you have is Rayleigh scattering, right? So that is happening from the air molecules, and the intensity is proportional to 1 over lambda raised to 4, lambda being the wavelength, right? That's why you see blue as the sky color. So if I now remove the atmosphere, if I now remove the air molecules, what should the color of the sky be? Blackish, okay. What about sunrise and sunset? What is the color at that time? Why is it red at that time? So at the time of sunrise and sunset, I am seeing the blue not there, but more and more of the red. Why so? Okay, so the sun is at the horizon, that's what she's saying. Okay, so now tell me, what will the color of the sky be, or what would the sunrise or sunset in Mars look like? Like if I am on Mars, what should the sunrise or sunset look like? Where there is no atmosphere. Okay, so that's what sunset on Mars, it's more bluish. It's exactly opposite now. Because of the scattering, it's not there, right? It's blackish blue. Okay, so many questions. When chemists ask questions, for example, we ask very different questions. So this is indigo blue, which is from, you know, the jeans that you wear, or rather I'm wearing right now. And we don't ask questions like the previous ones, but we often ask questions: why are some molecules colored? Why are others not colored? What gives indigo its color? What is the chromophore? How can I really change the structure here to get an indigo molecule of, let's say, purple color, or indigo molecule of red color? How can I change the molecular structure altogether? What will happen? But if I change the molecular structure, what will happen to other properties? Such that, will I be able to dye my genes with it? If not, probably that change is not good. So that's what most chemists are working on. And in fact, the bromine addition will give you that purple color. So these are the different ways people think about color. And very often chemists will talk about these transitions. So this is something you might have again studied, right? Everyone with me on this one? So what are these transitions? Okay, so pi electrons, so n to pi star, pi to pi star. Basically, electrons from their ground state are going to get excited to the, you know, higher energy state. They're going to come down, and that's what is going to give you that color, right? That emission. So now let us look at a few demos, and I want to talk a little bit more about colors in chemistry. So can we switch off the lights? Okay. Here. So I have some salts here, and we are going to put them on fire. Really trying to, you know, look at the flame colors, yes. Yeah. Can you all see the colors in this flame? Right? So different colors you can see because of the presence of these salts. There are various different elements present. Each one has its unique signature that it jumps to, like so from ground state to excited state. Yeah, okay, probably it might be better visible now. Right, so what do we have here? We have lithium and strontium. So this is strontium right here. That's lithium. Lithium is red. In the middle, we have some yellows, which are basically sodium, barium, and then the last one there is copper. Right? So you can see all of these colors very nicely. Again, the electronic transition is what we are looking for. Right? Everyone with me? So you can See that these are the colors that give rise to your fireworks. Yeah, it's mainly the methanol catching up fire, but because there are salts inside there, the electrons are getting excited and you can see nice colors coming down, right? And next time when you see Diwali fireworks, please pay attention to what color you're really trying to look at, because they're really fascinating. In fact, there are a few colors that we still haven't been able to figure out, in Diwali fireworks. So like a deep green, we are not able to see yet. So we are still on that quest. Now, you also have colors of the transition element salts. So copper sulfate, yeah, sure. No, so lithium, and that's what I was saying, like lithium and calcium, even if I think about the properties and their group structure, they are very different. But that's a good question. I may explore this further and get back to you. So it's a wonderful question, and people have thought about this part, wherein predicting the color of a compound, can we really predict it? Now there are some patterns that you see in a compound, chemical compound, and you can say, okay, this would be the color of this particular compound. But very often it is not a law that can be applied to the many compounds that we have. So for example, let me take the compounds of lead. Okay, lead, for example, lead chloride is white in color, but lead iodide is deep yellow, like really nice, shiny, golden yellow. So why is now there is a sudden shift between chloride to iodide? Bromide is again white, pale white. So why this sudden shift? So then you can think about the reason why it has, it is like this, and then people really apply Fazan's rule and then say, okay, that's why the color is yellow here, and so on and so forth. But if you think about the other way around, trying to predict the color of a compound, it becomes more and more difficult to come up with one law or one set of rules that will govern. Nothing that can be applied universally. For a set of compounds, yes, you can predict. So for example, copper compounds are mainly greenish blue. That's what we saw when Egyptians were trying to use it. That's the same thing here. Copper sulfate is blue. In fact, the next one that I was going to talk about, the crystal field splitting that happens in the D block metals. Again, you see a transition from lower energy T2G state to the EG state. Again, it's an electronic transition. Now, copper sulfate, has anyone seen what happens when you heat it? It becomes white. So why does it become white? It loses the water of hydration. So in fact, so for example, these are both chromium compounds, and this one has all ammonia molecules as ligand. Now you change one of them from ammonia to chlorine, the color changes tremendously. So copper sulfate, when it loses those water molecules, now you're removing all the ligands, right? And you're going to see a very different color. So that's why it's difficult to predict the color of a compound, because we have so many phenomena that can give rise to a color of a compound. And one of the things is conjugation. So the more and more double bonds that are there right next to each other, you have that particular compound as the colored one. So remember the chlorophyll structure, it had again a long range of conjugation. Here, beta carotene or turmeric has those double bonds right next to each other, or alternating double bonds, right? Okay, so when, let's say, and this is something that all of you have done. Let me just do this. This is an experiment that all of you have done in school. As I do this, what is happening here? So it was colorless before, and then I sprayed something on it and it became colored. And what is this? Any guesses? What is this? What is happening on the paper? Hey, come on, you all did this in school, right? What is happening? What is your guess? Okay, so it's an acid-base indicator. You all have used phenolphthalein. In fact, I had written the text with phenolphthalein and I just sprayed NaOH on it, right? Now, the reason why phenolphthalein gives you a colorless form versus a pink form, or rather a deep pink form, is because the molecular structure changes in acidic versus basic medium. And in fact, we do have that, at different pHs you're going to see two different compounds, okay? Or rather, I would say two different forms of the same compound. If I add acid, it is going to reform this bond to form this particular moiety again. And that's why you will not see that pink color anymore. So this is your pink color. Again, see, in the pink color, there is a lot of conjugation happening, a lot of double bonds right next to each other, which are absent here. Here what is happening? This particular ring is separate from this ring. There is no alternating double bond here in the middle. Right? So that particular compound is not colored. The long conjugation is going to give rise to that color. Everyone with me? Okay, so now I want you to observe. Okay, so what I have here is some NaOH. Again, we are going to talk about very simple science. So I have some NaOH, I have some glucon D. Two of the things that you probably have used, right? So I'm going to add some glucon D here. And I have some other compound here, which is called as methylene blue. Okay. Now, I just want you guys to make observations, okay? Tell me what is happening. Okay, so what is the color? Blue, okay? So let me shake it and let me keep it for some time. Probably, I hope I don't have to wait for a long time in this pose. And it works. It will work. Let's give it some time, okay? Okay, it started happening. Until then, tell me what happened here. The writing is gone. NaOH dried, is that the reason why? What if I spray on it again? What will happen then? Okay, so interaction with atmospheric what? Moisture. Will moisture, okay, remember what made the phenolphthalein that was pink in color go colorless? I need to have some acid, okay, so what is the acid that is present in the air? Do we have an acid present in the air? Carbonic acid is present? Okay, carbon dioxide is present, okay. Okay, now pay attention to this. What happened? It's now colorless. It was blue. Let me shake it again. It's back. What is happening? Okay, so this is what I meant by not remembering what science laws or rules are. Let's try to figure it out together. We have 5 minutes to answer this. Again, it is going colorless. Where is that blue color going? Is it settling down? So I need to look at, okay, can you tell her whether it is settling down or not? No, it's not settling down. Okay. See, but that's a good question. Is it settling down? Because that's what we have typically seen, is that pigment settle down, right? This one is not settling down. Can you make observations such that you can tell me what is happening in the bottle? Okay, so it was probably only when it was hot enough it was colored, and maybe we could monitor the temperature. So that's a wonderful guess. So again, she's coming up with a hypothesis. We could come up with an experiment. Temperature doesn't change much. There's not much kinetic energy. So let's say that I give you that answer. So what other hypothesis can we come up with? Okay. Okay, so she's saying the shaking is what is causing the change in the color. So let's shake it again. Okay, that's wonderful. So we do have, probably her hypothesis is true, but what is happening? So glucon D is completely dissolved. I don't think any particles are suspended anymore. But I can go on doing this, for forever. Can I go on doing this forever? Now the blue color is not as bright as it was. Okay, so we are now making an observation that is crucial. The blue color is not as bright as it was. Any other observations that will be helpful? Yeah. Wonderful. So the time the color is staying is also decreasing. So what does that tell me? Something is getting used up. Wonderful. So what is that thing getting used up? Let me do one more similar observation now for you. Let's see, let's do a variation. So I've taken exactly the double amount of that in this bottle and I'm going to add double the amount of everything. Okay. So nothing is changed as per the ratio of things. Okay. So 3 and, so I had added 2 spoons there. I'm adding 4 spoons here and there we had added 2 drops. So this is 4 drops. Okay, so nothing is changed per se. Now what do you think will happen here? So is this color going? Will it go? Air was needed. That's your prediction. Let's wait and see what happens as we put this again here. So she's saying air was needed. How can you make an observation that will test that the air was needed? If I open, no, okay, so there is air inside, right? Can you see a nice blue ring? I don't know whether it's visible, but where is that blue ring forming? It's only forming at the top. Why? Because it's in contact with the air, right? So I can see that this has started becoming decolorized again. So the first hypothesis was it will not decolorize, but it is decolorizing. It is decolorizing, right? But will it become blue again? Not as much, right? Because now there is no air. There is no air to make it go from colorless to blue form. So methylene blue here is a dye, okay? It's an indicator, a redox indicator, which is blue in the oxidized form, but it is colorless in the reduced form. In fact, what you had here, the glucose, which is a reducing sugar with NaOH, was reducing that methylene blue to its colorless form. The moment you shook this, you added oxygen again, or you made methylene blue get oxidized again to make it go to the colored form, right? And in fact, this is a test that is used in milk industry to check the purity or how good the milk is. So why does milk industry use this one? Suppose you get milk at home, suppose you have methylene blue and you add methylene blue. If the milk is good, what color should it stay? Should it stay blue or should it become colorless? What's your guess? Why? Huh. Okay. Okay, so let's assume that the milkman is honest enough. Okay, I'll take 2 or 3 more minutes. Let's assume that the milkman is honest enough and not adding water. But if the milk has gone bad, what happens when the milk goes bad? It gets, what gets oxidized? It goes rancid, yes, that it tastes rancid. So what happens in the milk? Why does it go rancid? So there are the growth of bacteria happens. Okay, so how is that going to change? What is it going to change? What are the bacteria going to need? They're going to need oxygen to grow, right? That means they've consumed all the oxygen, right? So when you add methylene blue, if there is too many bacteria and all the oxygen is already consumed, right? The methylene blue is going to quickly turn colorless, right? Whereas if it stays blue, then it is good milk. Probably the bacterial growth hasn't happened much. So when the milkman is pouring from the top, what is he trying to do? Like you must have seen that, no? They don't directly just pour it from the top. They're trying to add oxygen, right? So the idea is that, okay, so that's the methylene blue, that's the leucomethylene blue. Again, observe that the conjugation exists here, it's broken here. The color was observed because there was a conjugation double bond, alternate double bonds, right? Okay. Now, so far we have talked about color and how we look at color, how we perceive color. What is the, so which one is lighter according to you, A or B? How many of you think B is lighter than A? So now you might have seen this particular thing before. You were saying something. Go ahead. You raised your hand, right? Go ahead, tell me. Okay, so because your brain is thinking that there is something, that there's some shadow on it, so it should look darker. In fact, both of them are exactly the same shade. So when we perceive color, there is much more than, the exact shade and the representation. So when we are trying to map colors, again, do think of these things. So that's what I wanted to end with. In fact, I don't know how many of you can remember this dress. This took the internet by sensation, right? What is the color? Is it white and gold or blue and black? How many of you think it is blue and black? How many of you think it is white and gold? Okay, the true answer is it is white and gold. Right, it all depended on lighting. So this is the same dress being worn. So here you can see it's blue and black. Here it's, So the idea is when people were told that this is a wedding dress, suddenly people started looking at it as white and gold because somewhere in their brain they knew that it has to look white. So again, the idea here is that when we perceive color, it is not just, a combination of those RGBs. So when you have to actually come up with machines and AI to really train them, you have to think about all these things to come up with the best AI model. So now coming up with a machine that can actually perceive colors like humans, you have to think about various things, previous experiences, a person's age, a person's gender, how it would look like for that particular, in that light setting and other things. So coming up with the right model to look at color is not easy. Okay, so that's what I want to end with. Thank you. Yeah. Any questions? Many people guess that A is darker than B ideally, but then they say that, see, somewhere in your mind you also knew that I'm going to trick you, right? So there is, I mean, you do take that into account when your brain is making that judgment, but without any context, if this is shown to people, very often people will say that A is darker and B is lighter. Again, it has to do with the electronic configuration of each element and how the T2G and EG states are, are occupied with electrons, because the number of electrons in each element are going to be different. Their d orbitals are also going to look different. And that energy difference is going to matter to give you that color. Yeah. I don't think so. That's true. But I mean, because there is a huge industry that runs on synthetic color. Uh, Vibrancy in the sense like it should appeal to human eye, right? I mean, the Ferrari red is a synthetic color. It's very nice and bright and vibrant, right? Or for that matter, nowadays we don't also, we synthesize indigo or copper phthalocyanin. We don't really extract it from the plant. So most of the colors nowadays are synthetic in that aspect, that they are manufactured in industry rather than obtained from the natural sources. Okay, so again, there are 3 cones we have. So depending on which cone defect you have, different color blind people. So there are various types of 3 color blindness types, right? So each one of them is going to look at world differently. In fact, one of the resources that I've given here at the back, I'll point you to look at this particular resource. Wait. This one here, the medium beginner's guide to colorimetry. They have also mapped how this chromatocity diagram will appear to colorblind people. So what do they really see depending on the defect that they have? So let's say that the long range cones are not really active, then you're going to only see with the small and medium range cones, and that's going to really change the way you look at this particular chromatocity diagram. So they have mapped it for that person also. I would request you, this is a wonderful essay for all you math enthusiasts. It goes through all the mathematical operations that they did to come to the final current one, that is the CIE lab. The way Adobe uses it now, or most of our displays use it now. But it has taken years of mathematical journey to come to what we use today. So do have a look at that. So one of the axes is also, so in this case, it's right now 2D, but the third axis which is added is the 3D. Even then, it is very difficult to come up with the 1.5 million shades that human eye can perceive. So it's difficult to really map it and standardize it. But I mean, you get to the next best possible match is what I understand. Yeah.
Questions? Let's thank the speaker for shining light on the science behind colors, and let's
Thank
give
you.
her a big round of applause.